So hello everyone, welcome to our joint webinar with Oxford Ionics with Dr. Curtis Volin. We're super excited to have him here today. So Nullspace is a relatively new company. We're about 2 years old, but our technology has been developed in a defense contractor for over 13 years. And we develop software that essentially addresses the limitations of legacy EM simulation tools like HFSS, CST, COMSOL, FICO, and so on by providing faster simulations with high accuracy. As I mentioned, our solvers, even though we as a company is relatively new, our solvers have been developed and tested in defense industry for over 13 years and are finally available outside of defense industry as commercial products through Nullspace. So we have three main products, and Curtis will be showing you two of them today. So the software that's relevant to all of you on the call today is Nullspace ES, which stands for electrostatics. So Nullspace ES is the world's only commercial electrostatic solver for extremely large scale, rapid and accurate design and analysis of structures that support modern quantum computers, such as particle accelerators, and other electrostatic applications, and of course, ion traps. And that's what we're going to be talking about today. Nullspace EM is its sort of sister solver, but it's the electromagnetic solver. So EM stands for electromagnetics. It's fast, accurate, modern EM solver designed for electrically large problems, large optimizations, uncertainty analysis, and so on that are just not well handled by legacy commercial tools. So that's a fancier way of saying when your HFSS simulation crashes because the problem is too large, that's where Nullspace comes in and can handle that kind of simulation. And then finally, Nullspace Prep. It's our CAD and meshing tool. It's based on Qubit software that we know a lot of you are familiar with that integrates seamlessly with Nullspace ES and Nullspace EM Solver through a flexible Python interface. So with that, I'd love to introduce our presenter for today, Dr. Curtis Volin, who is a principal ion trap designer at Oxford Ionics. And Curtis is joining us. You're in UK, right, today? Curtis, joining us from UK? All right. Dr. Volin is a visionary in quantum systems development. He's a co-founder of Quantum Systems Group at Georgia Tech Research Institute, which he founded in 2005, and establishing as one of the earliest dedicated quantum computing research teams. Before he joined Oxford Ionics in 2024, he served as chief scientist for ion trap development at Quantinuum, where he advanced the development of scalable quantum computing architectures. Dr. Volin holds a BS in Applied and Engineering Physics from Cornell and PhD in Optical Sciences from University of Arizona. He's developed deep expertise in ion trap design, waveform modeling, and quantum systems integration. His work focuses on bridging theoretical quantum mechanics with practical engineering solutions, particularly in development and optimization of experimental ion trap quantum systems. So with that, it's my pleasure to hand you off to Dr. Volin.
I'm going to dive right in. I have a lot of content, and we don't have a huge amount of time, but I'm talking about precision ion trap modeling for quantum applications, mainly for quantum computers. So, next slides. Here we go. Okay, the Nullspace tools that Masha just described can be used essentially in three different ways. So, the first regime is optimization of trap geometry. So I have a picture like this at the right where I'm optimizing an electrode pattern for a junction, say, and I want to perturb the vertices that control the perimeter of these electrodes and see whether that's a better design or a worse design using some merit function. That is, the code can be set up to run quite quickly so that I can run essentially thousands of iterations of pushing vertices around using whatever optimization algorithm I want to use and get a good answer quickly. The next kind of regime is what I would call die scale design validation. So once I have all my pieces of my trap optimized, I want to put them all together and simulate this sort of at scale and see whether they all fit together correctly, whether this thing works as intended when I scale it up to a larger size. And then what I would call a production model, which is that once we have decided to fabricate a trap, then I would extract the geometry from a layout file, like you would get from KLayout, a GDS file, import it into Nullspace, and simulate that trap as precisely as possible in order to generate the data I need to make waveforms that go into the lab or do calibrations in the lab. So what I'm going to talk about today is something kind of halfway between 2 and 3, right? Is obviously I'm not using a real trap that anybody's made. I don't want to get into IP land. But I do want to show you kind of the knobs that you would turn in order to get the accuracy all the way up to production scale. Okay, so the trap that I'm going to look at today is based on the Peregrine trap. There's this nice archive paper that was published. I'm not going to exactly simulate this trap, but I think this is a good representation, because if I were going to design a linear ion trap, this is pretty close to what I would design. This is a great trap. Okay, so oh yeah, one thing worth pointing out is it's not a particularly the geometry here is pretty much planar, right? It's not a geometry that would stress say a gapless plane approximation all that much, but I just wanted to have a simple trap to simulate for the sake of this demo. But everything that I'm showing you would be equally useful for simulating traps like this, right? For which there is no comparable code that can even begin to simulate what is going on in these traps to the level that I would really like to have in order to generate waveforms and do flight analysis and things like that. So all the things I discuss are perfectly applicable to this. I grabbed a couple of figures from the paper just to show you roughly what I'm simulating. I think the dimensions here are fairly well given, but there's some ambiguity, for instance, about different gap widths and so on, and there's no information about spacing between these layers. But the key thing to point out is that I have some top metal here, and then I have, at some distance behind that, I have a ground plane, and that's most of the geometry that I'm going to try to capture. Expect my null height to be about 74 microns above the trap surface, the top metal top surface. There are segmented electrodes with a pitch of 70 microns. There is an outer electrode that is cut up in the real trap, but I'm just going to treat it as a single electrode here. And then the whole isthmus is about 1.2 millimeters wide. Finally, there is a load slot. There's a quite small load slot located off to the left of the trap. It's 13 microns by 140 microns wide. All right, back to Masha.
Okay, we're going to go ahead and switch to our demo.
Now we can go ahead and go to Nullspace and start to generate the model. So I have a script over here that I've got prepared ahead of time that will give me all of the basic geometry. Hopefully we can share that script so that you can see it, but we generate the upper half of the top metal of the trap, and that's just the top metal plus a ground plane below. The ground plane is contiguous instead of being located just directly underneath the gap areas as was drawn in the paper. I will explain that a little bit more later on, but just looking at some of the dimensions of the trap, if I look at the properties here, this curve is length is 600 microns, so this would be a 1.2 millimeter isthmus. The entire trap model is 3.4 millimeters long. I just truncated this at some arbitrary point without putting a whole lot of thought into it. Obviously, we can simulate things that are much larger. The outer electrode is 150 microns wide. Our electrode is 76. I just kind of rounded off some numbers for my own convenience. This electrode is 40 microns wide. If I go look at one of these electrodes, you can see the pitch is 70 microns. So this guy's at x equals 0. This one's at 70. And then we have this load slot down here, which is which is 13 microns wide, and you can see from it being about 2 electrode pitches that that is right about 150 microns long. So I want to skip ahead a little bit and look at meshing, just to motivate the next bit of what happens with geometry. So I'll talk more about this later on, but I'll run the mesh commands and then just mesh a couple of these surfaces. So let's grab this guy. So mesh that surface, and then mesh this surface as well. So now is when it's good to have just a little bit of insight into what Nullspace is doing when it solves the model, right? So for each electrode, it applies 1 volt to this electrode in simulation while keeping all of the other electrodes grounded. And then it calculates the charge distribution on each of these triangles, assuming a uniform distribution on each triangle that's consistent with that 1 volt of potential. For those of you who are familiar with the gapless approximation, it leverages the fact that when these gaps are 0 microns wide, the actual charge distribution is an impulse, right? It's just a line charge around the perimeter of this electrode. And so then it just integrates along those line charges to get the potential and electric fields above the trap. In our case, these gaps have some width to it, and so this charge is not a line charge. It's sort of blurred out a little bit, but it's still essentially a line charge. And so we want very tiny triangles near the edge so that the simulation is accurately reproducing the physical reality. And we don't need such big triangles in the center because at that location, it looks more like a capacitor, right? We have a uniform charge here, and we can have quite large triangles and be reproducing reality. So the mesher is quite good at simply just telling it what the size of the triangle you want at the perimeter. So in this case, we picked 2 microns, but that's a number you should study for your own particular purposes. And then tell it to make each successive triangle slightly larger. So I think the default in this case is 1.3 times. So each time it goes another row back, it makes the curves around the edge of the triangle 1.3 times larger. And so you have this kind of exponential growth in the triangle size. The same is happening on the ground plane below, right? As we have these curves and we have these tiny triangles, but these triangles are getting bigger all the way across here, so that they are much, much larger out here. Since this is a ground plane, we know physically that there's going to be an image charge present as a result of the line charge that's present in this electrode, and then it's going to have almost the exact same structure. It's going to be something that looks like a line charge, but you see that because of the structure of these giant triangles underneath, the solver won't be able to create that physical reality. It'll be stuck trying to solve a line charge in these huge triangles, and it'll fail. The evidence of that will be that it takes a long time to converge, and also it will converge to a bad answer. You will have a bad simulation result. So we want to actually cut up this lower ground plane into pieces that match the upper ground plane, so that it will mesh triangles that aren't necessarily identical, but are similar in scale as you sweep across this trap. So delete the mesh that we have, and then we want to do a imprint command. So we go to where those commands are located in the script. Sorry, I got lost there for a second. So we're just going to imprint every curve in the top plane onto the surface below, and it knows the surface normal, so it does this imprint with a single line command. And there you see that now the top metal structure is reproduced in this lower ground plane. Note that the ground plane is only underneath the portion of the trap that is near where the ions are. We don't need to have that ground plane out here. It's not going to affect the fields that are present. in this part of the trap, and that that removes metal that you don't need for the simulation. Next thing to do is sweep all of the curves to emulate the thickness of the metal. So now we've added a 1.5 micron thick sidewall to all of our top metal electrodes, or at least the electrodes that are close to the ion again. So for instance, out here, we didn't put sidewalls on these electrodes because they're so far away that they simply will have no effect on the fields that the ions see here. The next thing to do is sweep the curves in the load hole to produce the load hole, and I've sort of figured out ahead of time what all of these curves are, so I can just type this in and you see that it makes all these surfaces. That is, the back of that is 50 microns down, as was specified in the paper. And then the last thing I want to do is sweep the sidewall of the die. So I'm going to take this curve out here and sweep it down to the thickness of the silicon substrate, which is something like 700 microns. In this case, 600 is all I did. And so now, we're sort of emulating a chunk of an entire trap. And in fact, we could add the geometry out here at the ends, but it's not especially important to do that for the sake of this demonstration. So I'm going to run a few commands that simplify the geometry. I think the main thing that does is replace each of these independent surfaces here with one big surface. Notice that we still have a curve here, right? It doesn't recognize these two curves, even though they abut no angle, or these two surfaces, even though they're next to each other as being a single surface with a curve at the end. So we will get extra triangles here that aren't necessarily functional from a solve perspective. You can do this thing over here called compositing. I could composite these two surfaces, in which case it'll remove that curve virtually, right, and not put small triangles there. In reality, I found that the meshing is less reliable when you put composites into the model. And so the small price you pay in terms of solve time from having a few extra triangles is more than worth it, compared to, especially the larger models, potentially having mesh errors generated that are very, very difficult to find and diagnose. So I'm just going to leave those off. And then I can colorize things to make them consistent. So we have pink RF, green and beige for the control electrodes, and this gray color for the lower ground plane. So the next step is blocking. So we have to create blocks, which are an entity type that can contain surfaces. And so we want Nullspace to know that when it puts 1 volt on this electrode, that it's going to take all the triangles that are present in these 5 surfaces, the top and the 4 sidewalls, and put 1 volt on all of those surfaces. And the way to do that is to assign all those surfaces to a single block. And so what you can do is just go in and click on the surfaces, and it tells you the surface number. And so I just click through those in order. And then you can use a script in whatever your favorite language is to convert that into the blocking commands. I've done that ahead of time, of course, and we generate the blocks. See that block 1 is the RF electrode and its top and sidewalls. Block 2 is all of the grounds, including the load slot here, the lower ground here, the sidewall there, and the top metal ground there. Block 3 is the first control electrode. And I have all of these in order as you go down the line, all the way to the end, and then the outer electrode. You don't have to put those in any particular order. It's just kind of a convenience. So the final thing I want to do is make sure that all of the geometry got allocated to a block, that there are no blocks remaining. It won't throw an error if you leave any surfaces out of a block. It will just treat them as independent blocks and just append them to the end of the file. In this case, we just take a dummy block and try to assign every single surface to it. It throws a lot of errors because the surfaces are only allowed to be in one block. and they're already allocated to blocks. And you see, in fact, that this block 999 was not created, which means that all the geometry was correctly allocated. I did the imprint down. Notice that there's a mismatch here, is that I have a curve in the lower geometry corresponding to the end of the ground plane, and it's not in the top metal ground plane. So I'm just going to fix that really fast by imprinting up. And so now that will match. It's not as big a deal as the other way because there won't be any small, there won't be any line charges there, but it's still worth doing. I can do a simple command here to look for any curves that are anomalously small. I would expect the smallest curve in this model to be 1.5 microns, which is the thickness of this metal here. And I can just do an explicit search. I can say, ask it to show me any curves that are less than something smaller than 1.5. It throws me an error telling me that those curves don't exist. But sometimes, particularly when you import a geometry from a layout file, like you would get from layout software, you will get snapping errors. So you might have curves that are 5 nanometers or 1 nanometer long from a snapping error, and they're impossible to see as you're sort of traversing this model the way I'm showing you now. But this command would catch them quite easily, and you would go in and fix those. So now we can go back to meshing again. This is one of the most powerful things of this software, and the main reason you want to use it is that it generates this adaptive. I think it's probably not the right word, but it makes triangles that grow as you move away from the edge, and that's very well aligned to the physical reality of what we're trying to simulate. All we have to do is tell it to make triangles, and then define the curve size on the edges and let it fill in the rest with a single line command. So we're just going to run that. Should take only a few seconds to generate the complete mesh of this model. It's telling me that. All right, so there's our complete mesh. You could spend a lot of time like going in and saying, I can make the curve size bigger on this curve and not have as many triangles there. Clearly, there's going to be no charge on those triangles out there, or even out here, I don't care as much. What I've found is that kind of effort doesn't really pay off. You might spend quite a bit of time manually tuning the curve sizes, but it might actually, even if you choose something that's well aligned with the physical nature of the charge distribution, it might still take longer to solve. So now we have a complete model, although you'll notice there's still only half of the model drawn. And the way we're going to make that enough is by taking advantage of the symmetry planes that are available in Nullspace. So when you look at the deck file that we use to run the simulation, it has these symmetry plane options. We have a symmetry plane at y equals 0. That is the geometry that is in the minus y half plane is identical to the geometry in the plus y half plane. And so we can simply tell Nullspace to impose that symmetry, right? For every when it does the charge solve, for every charge that's present over here in a triangle, it's gonna make a virtual triangle over on the minus y plane that has the same charge. That's even symmetry, or it's going to make one that has the negative of that charge. That's odd symmetry. So we're going to run 2 simulations. The first one has the even symmetry, so that corresponds to having a volt on both this electrode and its mirror electrode. And we're going to run odd symmetry, which corresponds to having 1 volt on this electrode and minus 1 volt on the mirror electrode. Then in order to get the potential of just, say, the electrodes in the plus y plane, we take the sum of those 2 models. And in order to get potential in the minus y plane on those electrodes, we take the difference of those two models. And then we have a complete set of data. The advantage of doing that is primarily in runtime. The runtime of the model is generally proportional to something like the square of the number of triangles. That kind of depends on how much time is spent solving for the charge versus how much time is spent then solving, filling the potential in above the trap. But you can see if we make the model half as big, that maybe it takes about a quarter as long to run. We have to run two models. So if they're run serially, then it takes still half as long to run. If they can run in parallel, then you've saved yourself quite a bit of time. It's a quarter. In a lot of the really, really big models, we might be memory limited. And so having a model that is half as big gives you substantially less memory requirements. Again, something more than linear. So you can run a much bigger model using the symmetry. If your model has symmetry in the x plane as well, if the plus x is the mirror of the minus x, then you can run just a quadrant of the model and run 4 simulations. Again, if you have the licenses to do that, that can take you essentially like 1/16 of the amount of time to run. This trap does not have that symmetry. The load slot is off to one side, so we can't use that. And then there's a remaining ground plane, which we can have in the z direction, which you could allocate to either placing a ground plane at the location of whatever the circuit board or interposer is down below this die, or by placing a ground plane above it, simulating sort of mesh that's often used in experimental groups to form a Faraday cage above this trap. You can choose which one is more valuable from a simulation point of view. If they both need to be present to get the kind of fidelity you want, then one of them can be virtual and the other has to be physically inserted into the model and meshed in order to have that capability. So the other advantage of doing this symmetry plane is that we know that the potential distributions in the volume above this will be perfectly symmetric. That when I go in and try to find, for instance, the RF null in this case, that it will be located perfectly at y equals 0 to numerical precision, as opposed to sort of wandering around at the fidelity of the model, which is, I'll show you later on, is quite good, but it still gives you a little bit of an advantage there. Now we can go ahead and take a look at the input deck that we're going to use to run this model. Of course, there are 2 of these. One is for even symmetry in this plane, and one is for odd symmetry in the y plane. All the other settings are the same, so we can just look at one of these. I've chosen to put a Z symmetry plane at 2 millimeters above the trap. This would simulate a Faraday cage located above the trap. Then in the solver settings, we're going to use a compress rather than a full simulation. Dense, I guess, is the other option. This is not a particularly big model. I think it has only on the order of 160,000 triangles, and so it could solve dense on a reasonable size computer, but it would take a lot longer probably, and we don't really lose any precision here by using the compress if we do these other settings. So we're going to go ahead and use compress. The first thing to do is to switch the precision to double. I think the default is either hybrid or single. I'm not sure which. But that will be very limiting in terms of the precision of the electric fields generated from the simulation. The fill and solve compress tolerances are set by default to match single precision. To run in double precision and really take advantage of that, we need to set these much tighter. The default is 10 to the minus 4. We're going to go all the way down to 10 to the minus 7. You might think this would take a whole lot longer, but the convergence is exponential, and so it might only take 10% longer or even faster to get this much more precision in the result. In the output block, I have completely custom code on the back end for taking the raw samples produced by Nullspace, the potential and electric field samples, and converting them into storage and subsequent sampling for the fields and potential and further derivatives in the volume that we sample. I'm not going to cover any of that in the context of this discussion. All I point out here is that a nice convenient thing is that I can insert comments into the input decks. And in this case, I'm giving my codes downstream an instruction about which electrode to treat as the RF electrode in doing the subsequent sampling. Okay, so I ran that ahead of time. I don't have the time to sit here and wait for this to run during the course of this talk. So let's look at the output deck that was generated. Again, there are two here run serially. So the first one is even and the second one is odd. I ran all 24 electrodes, including the ground plane, which you don't always want to run, but why not? It doesn't take a whole lot longer. It kind of gives you some memory predictions. None of these are particularly valid. The compressed memory is usually better than 95%. And so we can run this thing on quite a small computer. Even with dense, you can run this on a fairly small computer. The runtime, the solve time. So this is the time it takes to actually generate the charge distributions for each of the 24 input electrodes is just over 10 minutes. The subsequent fill only takes about 7 seconds, or not fill, I guess that's not the right word. The post-process, the creation of the samples in both potential and electric field takes about 7 seconds per electrode. And the total runtime is just around 14 minutes. You get the same for the other symmetry.
Okay, great. Thank you. So that concludes the demonstration portion of the webinar. And now we can go ahead and open it up to additional questions. So Curtis is going to come on here and he'll be able to actually answer your questions.
Yeah, so I'm going to look at some of the results of that simulation real time here. I have a couple of questions that I can look at. Support for parallel execution. So Nullspace Prep, I think, is predominantly single threaded. So for some of the very, very large models, for instance, it can take quite a while, or minutes to do the meshing, but because the meshing algorithm is so powerful, like that is for models that have 2 million or more mesh elements. So that's actually not all that long considering how often you really need to do that kind of simulation. And the Nullspace, the electrostatic solver will automatically take advantage of every single resource on the computer you throw at it. So it will parallelize over all of the cores available to it quite efficiently. Can you plot fields inside of Prep? The answer to that is no. I use entirely my own custom backend, but there are quite a few tools within that are provided along with Nullspace ES that allow you to do visualizations and some processing, plus some nice integrations to Paraview for visualization. Yeah, so compared to CSV and COMSOL, what do you find most useful in your work using Nullspace? I think that'll be pretty obvious once I start talking about results. So let me just jump over. And so I'm going to run this program real time. All it's going to do is take the output fields that were generated by Nullspace and go sequentially along the length of the linear trap and calculate the location of the RF null and some of the properties of the fields of that null. And I'm going to go ahead and plot this. This should only take a few seconds. This is just a business laptop, so it's not incredibly fast or powerful. So I generated a few visualizations here. The first one, as I sort of talked about in the video, was saying that that the Y position, the cross-axis position of the null, is going to be limited by numerical precision because because of the symmetry plane, and you see that here, right? It's found the location of this null to this is in microns, right? So less than femtometers. So we can kind of just ignore that in practice, right? It's perfect. We're much more interested in the other dimensions. So let's look first at what the actual real pseudopotential is along, well, real pseudopotential isn't really what the residual pseudopotential is along the null as we go from one end of the trap to the other. So the trap is centered at x equals 0, and it I think it terminates at something like I had a picture here, so I can drag it over just to get these dimensions. It terminates somewhere around 800, 1.2 millimeters, I think was the answer, and then the control electrodes stop at around 800 microns, and this load slot is right around minus 560. So then when you look at this pseudopotential, and this is for, I should point out, this is for using a calcium ion, calcium 40 with a RF frequency of 60 megahertz and an RF voltage of 150 volts. So, the first thing, the biggest thing you see when you look at this pseudopotential plot is this kind of like V-shaped structure with a very, very deep null right at the center, where you would expect it due to symmetry. This shape is dominantly showing you the results of truncating the RF rail at that 1.2 millimeter distance, right? In most labs, we're just never going to see pseudopotential below 10 to the minus 6. So that's kind of telling you this is a great trap, right? We have this huge range where that pseudopotential level is well below what's observable in the lab. In fact, this feature here is the load slot, right, where we have where we would expect to see some pseudopotential bumps around the load slot, but because Sandia can make such a tiny load slot, it barely impacts the pseudopotential in this range. So it actually doesn't really even rise to observable level. When I go over here and look at the ion height, so this is the null height along the entire trap as well. You see that it's pretty close to the 74 that they expected. It's a little bit lower than that by about half a micron. But then when you get this sort of parabolic shape that again is a result of the fact that the rails terminate somewhere 500 microns to the left and right of this plot, and so we have not perfectly flat height, but a little bit of shape to it. There are a couple of features here that are quite interesting. You may have never seen features at this level of precision using the kind of code that you're simulating. These are only nanometers in height. We have this funny waviness. And so you notice the pitch of this is 70 microns. So what you are actually seeing here is the result of the fact that there are gaps in the control electrodes that cause there to be wiggles in the height, and also the same wiggles here in the pseudopotential at the pitch of the electrodes. Of course, this would never be present in a gapless approximation. We would see a perfectly smooth curve here because it can't actually see those gaps at all. I admit this is a feature which essentially is irrelevant at the scale of what you would actually need to successfully generate waveforms and flights, but it's just kind of interesting that it's there and gives you a sense of the level of precision that we're dealing with in the results of this model. The biggest sort of morphological feature that's interesting here is this dip. This is maybe about 300 nanometers, so 0.3 microns. It's a pretty big dip. That is located over the load slot. And again, this is a very tiny load slot. You would certainly observe that kind of difference when calculating waveforms. You would see what looks like a stray field if you were using a gapless approximation and generate a waveform. And in fact, this I think is a key difference between what you would see, for instance, using a gapless approximation and trying to simulate a load hole or a hole in your trap versus what Nullspace is giving you. So you see that there's, in reality, because there's no ground plane underneath that portion of the trap, the ion height drops. If you, in the gapless approximation, just fill that with the ground, you would actually have the opposite sign. So you would actually have a bump up in the simulation because of the fact that the RF rails are ever so slightly further apart in that area. perhaps. Well, in this case, it would just be flat on through. So no, so there are two output products really. Nullspace ES is essentially two separate codes that are packed into one program. The first one calculates the charge distribution, and the second one calculates the potential and electric field at the sample points that you tell it to calculate from that charge distribution. And so I am using both portions of that. In particular, the post processor, the sampler, is extremely efficient in terms of computational resources. You would not want to do that yourself. And so like you can go in and plot the charge distribution. I grabbed it for one, and plot it in Paraview directly. So you just take the file that was output and you drag it into Paraview and click a couple things, and this comes up pretty much instantly. So you see the nice view of the charge distribution. But then you also in the same file, or not the same file in this case, but in the output file that it produces, you have the fields. Right now, a single simulation would have to run on a single machine. If you want something different than that, you have to talk to the Nullspace team.
Yes, and we are working on that. It is on our roadmap to create HPC licensing structure as well. So if you're interested in that for your particular application or your particular company, please reach out to us. I'll give you our contact information once we're wrapping up the webinar.
So an electrostatic solver, of course, cannot estimate what that would be, right? We're only dealing with perfect conductors, and in static regime, you would have to use HFSS or potentially Nullspace EM to simulate that sort of thing. For the regime of traps that I've designed, those kinds of simulations show that there really isn't phase lag. Perhaps you could design a trap so bad that it actually had that phase lag, but that's up to you. So that is, I think, one of the trickiest questions that exists in the context of ion traps, because you have a very, very limited ability to measure in an ion trap. You're pretty much stuck with what the ion can measure wherever the ion can go. And so, you're down in perhaps cryogenic temperatures and ultra high vacuum, and you don't really have the ability to probe all that well. However, right, once, when you can make a really high quality trap that does not have a lot of charging going on with it, you can just go in and measure stray fields and see whether they are indicate a great inconsistency with what the simulation is producing. And I think down to essentially the volt per meter sort of level, I think that work has been done in my experience, and really validated these models quite well. So my experience goes back quite a ways. I started doing this work easily a decade before Nullspace existed, and so like I have a little bit of an advantage in terms of working with these fields, and in particular, codes I worked with before that had much more noise in them, and so I had to do a lot of spatial filtering to get better performance. I'm also very concerned with compression, right? Is if you just want to generate large amounts, very highly precisely sampled potentials and fields on traps that are extremely large, you start looking at having potentially hundreds of gigabytes or terabyte sized files. And so compression was a substantial part of what I was considering when creating these codes. They're not, no physicist would be surprised by what I am doing, right? It is essentially I don't want to go too much into detail on it, but it's essentially predicated on the concept that if you know the potential on the surface of a volume that contains no charge, then you can calculate the potential everywhere within that volume. So basic electrostatics and a little bit of mathematics, and you can convert that into a reality. Me personally, I've not really used COMSOL for this kind of electrostatics, but I'm familiar with other people's work in this area. So I can answer that question in two ways. One is in terms of intrinsic capability or precision, and the other is in terms of workflow, right? Is the workflow of Nullspace is radically easier than using something like HFSS. HFSS is designed to simulate and interpret within its own GUI, and it's kind of very difficult to extract data from it and process it on your own. Nullspace is designed around making that data extremely available to you so that you can process on the back end however you want with whatever custom scripts you want. It's incredibly easy to access the data. In terms of precision, right, that most of those other codes, well, in fact, I think all of them that work that we've talked about, right, are finite element codes as opposed to boundary element codes. So the amount of precision you'll get from those, you'll see features like this, but they won't be real features, right? What you're predominantly seeing there will be the imprint of the finite element mesh onto the results. So you'll see all kinds of wiggles and movement here, but it's simply the result of the fact that you get non-physical field at the edges of the, at the mesh boundaries. And so if you try to do things like full flight, full time domain flights of ions within these fields, then all you're measuring essentially is the mesh that's underlying it. And making that mesh small enough to reproduce this kind of result is simply, it's orders and orders of magnitude away from what's feasible even with the largest computers that are available.
Awesome. Thanks, Curtis. That wraps up our webinar, and I just want to make sure if you were interested in what we talked about today and you would like to experience Nullspace for yourself, you can go ahead and schedule a demo with us of Nullspace for your particular application today. So if you go to our website, there is a contact button that says contact us, and you can go ahead and just fill out your information and we'll set up a demo for your team and your organization so you could see the power of Nullspace for ion trap design for yourself. And with that, I'd like to thank everyone. I'd like to thank our speaker, Dr. Volin. Curtis, thank you so much for being here. And any additional questions, reach out to us as well. An easy way to do it is info@nullspaceinc.com. And we hope to see you in our future webinars.